in terms of what to do when you're designing your high voltage power supply. Okay, so we'll start with the outline first. For this, we're going to start by defining not only creepage and clearance, but also some other critical terms which are closely related. Then we're going to introduce different insulation grade levels and how to select reinforced or basic insulation. Then we're going to do a flowchart with some examples of popular end equipment and how to select the spacing for those given end equipments. And then finally, we'll talk about insulation systems for user safety, but also for high voltage spacing and functional versus proper operation regarding high voltage. Okay, so if we start, high voltage is actually not far from us in our everyday life. There are many, many applications which we see every day in which we deal with high voltage. So some examples: electric vehicles, Class D audio, adapters and chargers. So how many of you have your laptop with you today with the charger? So a lot of people. I have mine up here. There's high voltage power that's there, and inside that case there are special spacing requirements. And what we're going to find today is how to choose those spacings, what rules to follow, and some special cases where maybe I need to get a little bit more aggressive in my spacing, and how could I do that? Some other examples: server telecom power supplies, power tools, refrigerators, all of your home appliances, renewable energy, solar panels, EV, and even lighting, different LED lighting, solid state lighting as well. Okay, so let's start by defining a couple of terms. So the two most important terms that we're going to talk about today are creepage and clearance. So the first one on the left side, on the left side, is creepage, and it is defined as the shortest distance along a surface of a solid insulation material between two conductive parts. So if I'm looking here, I have two conductors here, so one here, one over here. The creepage distance is this distance which goes along between the two, along this insulating material. When I talk about clearance, clearance is the shortest distance in air between two conductors. So in this case, it would be right here, the distance between this in air. So the parameters that impact creepage and clearance are also a little bit different. So for creepage, the most important parameters that we want to look at are pollution, humidity, and condensation. We will talk about all three of these and how they relate back to the creepage distance. For clearance, the most important parameters are the transient overvoltage, the pollution degree, and the altitude. So if you're at different altitudes, then the distance needs to be accounted for differently because the air will ionize different with a high voltage. Okay, so looking at creepage and clearance, there is no physical relationship between the two. And in fact, go back here. In fact, the distance between the two could be the same given the way that the spacing is working. Another key point here is that the distance is the shortest path, and that's not always over the top or under the bottom of the package. It could be around the outside of the package as well. In general, there is no case in which the creepage can be less than the clearance. And you'll always want to try to maximize both whenever possible. It's a trade-off between the size and the cost. Okay, let's first talk about material groups. And when we talk about material groups, we're going to use something that's called the Comparative Tracking Index, or CTI. So when I say CTI, what does that mean? Basically, it has to do with the maximum voltage at which an insulation material can withstand 50 drops of contaminated liquid, and this contaminated liquid is a solution of 0.1% ammonium chloride. So I'm applying a high voltage across my board, I'm dropping this contaminated liquid onto the board, and I need to see how much voltage I need to raise this, the voltage by, before it starts to provide a conduction path. So as long as the current stays below 0.5 amps, I'm going to keep increasing the voltage. So this is going to lead me to a number of different material groups, and we've listed those here in a table. So material group 1 is any type of material which can withstand higher than 600 volts RMS. So typically you will see material group 1 are packages that are on semiconductors. For example, an isolated gate driver from TI. The package would be made from material group 1. Material group 2 is between 400 and 600 volts. Material group 3A is between 175 and 400 volts. Material group 3A is important because this is generally the material that PCBs are made out of. So standard FR4 material for PCBs is material group 3A. And what you'll see as we go later into the presentation, because we're going to use components with different material groups in the same system, we need to take into account some other factors as well. And then the last one on our table is material group 3B. And material group 3B is between 100 and 175 volts, or if it's not specified, then we consider it to be material group 3B. Okay, the next important topic for creepage is the pollution degree. Now when I say pollution degree, I'm not talking about the air outside. We're talking about on the PCB itself, whether there is liquid or dirt or other types of things that are contaminating the surface of my system. So pollution degree 1 is the most strict. This is sealed components, inner layers inside of a PCB, anything that's inside of a clean room, anything that's inside of an environment where it is sterile or there is no moisture. Pollution degree 1. Pollution degree 2 is there could be some temporary conductive because of occasional condensation. So this could be your lab environment. This could be a telecom enclosure system. Pollution degree 3 is subject to conductive pollution. So this is an industrial setting. This is an unheated factory. This could be farming equipment or other rooms in which the condensation or temperature is not controlled. And then finally we have pollution degree 4. And pollution degree 4 is outdoor applications. So this is going to be the most harsh environment. Okay, let's talk about the transient overvoltage category. So the overvoltage category, also referred to as the required impulse withstand voltage. So there are 4 categories for the higher overvoltage level. And it has to do with how close you are to the energizing source. Now, when we say the energizing source, basically we mean where the service is coming into a home, for example. So category 4 is the original installation. So this is the wires on the pole outside of your house. This is the service wire going there. This is the e-meter that's connected to your house, to your building, to whatever situation we're talking about. Those are category 4. And these need to typically have up to 4 kV peak transient overvoltages. Now, category 3 is then the fixed insulation where the availability is subject to special requirements. So this is once we have the service coming into your house, this is the service panel. These are outlets that are connected directly to that distribution panel. Now, if we look at category 2 are plugs and various other items that are over a certain distance away. So these are outlets that are 10 meters or more away. And what you can see about these categories is as we get further away from the original installation, the transient overvoltage is going down. So for a category 3 source, we only need to have 1.5 kV peak transient voltage. Now finally, category 4 is category 1 is another appliance that's connected in which there is an additional isolation. So this could be 24 volt AC, maybe for a sprinkler or a thermostat, something like that, or it could be an adapter that's plugged in as well. Okay, we're going to talk about a lot of different standards today. So I don't want you to get confused with all the numbers. There's a lot of them. Nobody's going to remember them all. I don't know them all. The good news is we have a lot of references, and we've included all the references here. So don't feel like you need to memorize all of these numbers and all the different situations. That's the whole point of this presentation, so that we can share this information and make it easy for you to find what you need. So I wish that there was one single solution that I could just give you and it applied to every situation. Unfortunately, that's not the case. There is no single solution for different end equipments. There's different voltage classes. There's a lot of different things that we need to take into account. So, but to summarize here, we have 2 major categories. The first one that's listed over here, this is based on user safety. So all of these IEC standards that we show over here for creepage and clearance are for user insulation and user safety. The second column that we listed over here is for the PCB, and these are for high voltage spacing and for proper and reliable operation of the circuit, not necessarily for safety. So there are a huge number of IEC standards, and every end equipment basically has its own standard. So we've shown a few here. So IEC 60664 is the first one. And this is the most common one in which creepage and clearance are actually defined. And this is kind of a standard one that's used if you don't have another special one for your given end equipment. If the end equipment that you're working on is telecom, server, audio, communication equipment, then you need to use this standard, 62368. Some of you might know this number, 60950. That's the former standard. That one has been retired. If you're working on motor drive, we have this one, IEC 61800-5. If you're working on solar, there's another one. So you can see, depending on what equipment you're working on, there are many, many standards that are available. Okay, if we look at the PCB then, again, a lot of IEC standards cover proper PCB creepage, clearance, those types of things. But an important one to look at here is the IPC. This is the Institute for Printed Circuits. So general requirements are given in IPC 2221. And specific to server and telecom market, we have IPC 9592. Again, there are so many of these different standards, numbers. Don't try to memorize them. Just know where to find them and know which tables to look at. And hopefully through this presentation, we'll make it a little bit easier. Okay, so if I look now then at creepage and clearance insulation parameters that really matter, which ones do I need to look at? Which ones should I really care about? So we're going to start with user safety in an insulation system. Not every insulation-related parameter matters. So we need to take a look and see. For example, the component standards for insulated products, such as an isolated gate driver, IEC 60747, UL 1577, they're just addressing the insulation barrier to withstand electrical and mechanical stresses. They're not addressing creepage and clearance for safety purposes. So you still need to do other things within your system to make sure that it's safe for the end users. So if I'm looking at insulation grades, and the ones that we see most often are basic, reinforced, and functional insulation, creepage and clearance for those do not matter. That's not what we care about there. For those, we care about user safety. And so what we're going to see over the next few slides is what that means for proper functional insulation and for proper use of the circuit. Okay, so when I talk about types of insulation grades, so the first one that we're talking about is functional insulation. So that's this top one, functional insulation, or PCB high voltage spacing. So this is for proper functioning of the circuit. So maybe we have a high voltage gate drive circuit in which we need to isolate it from the low side gate drive. And this one, the spacing that we use, the creepage and clearance that we use is only related to proper operation of the circuit. It's not related to safety, it's not related to any other parameter other than just the circuit functioning properly. If I look at basic insulation is a single level of insulation to protect the user from electrical shock. So both normal and abnormal operating conditions. So for basic insulation, it's a single level of protection. If I look at supplementary insulation, this is independent insulation applied in addition to basic insulation. And we have two types of these. So it could be double insulation. So double insulation is the basic insulation plus a supplementary for single fault condition. And then the second type of supplementary insulation is reinforced insulation. And it's a single type of insulation that provides double the protection, so double the ratings for insulation. So let's take a look at some of the guidelines for insulation and how they are used to protect an ordinary person or user against electrical shock. So the first thing that we need to define and look at are the energy source classes. So we have energy source class 1, 2, and 3. And so these are defined by different IEC standards as well. And what we've shown here, we have energy source class 1, 2, and 3, and then from the different standards, what those particular voltages are. So within energy source class 1, these are the basically lowest voltage. We call them SELV, or safety extra low voltage is what this is called. And it's basically 60 volts RMS or below. These are what is deemed to be safe to touch without electrical shock occurring. So for those operating in SELV1 or TNV, we don't need to have any insulation between this and the ordinary person or the user. If we look at energy class source 2, that's basically 120 volts peak. This is related to telecom network voltage class 2 and telecom network voltage class 3 as well, over here for ES2. So for those, we need to have basic insulation provided here. So basic insulation between these voltages and the end user to protect them for safety purposes. And then we have ES3, which is considered hazardous voltage, is above 120 volts. And for those, we need to have supplementary insulation, which can be achieved by reinforced isolation. Okay, this is a table that comes from figure 2 of the IEC 60950-1. This table I find to be very confusing. So I don't really like this table, but we're going to talk about it anyway. On the right side, we have a table in which we've explained some situations, which I think makes it a little bit easier to understand this figure. So what we have are different energy source classes shown here, and what needs to happen if you have those energy source classes and a similar circuit, or going between energy source classes. What type of insulation grade do we need to have? So for functional insulation, if we're going between safety extra low voltage and safety extra low voltage, like from here to here, we just need to have functional insulation. That's, again, just to make sure that the circuit is operating correctly. If we have less than 60 volts, also, that's functional insulation. So, if we look here to basic insulation, an example that's given here is we have an earthed safety extra low voltage, which is here, earthed safety extra low voltage, or one of these TNV2 or energy source class 2. For those to go between here and there, we need to have basic insulation. And then for the reinforced insulation, we have more examples shown here as well. Whether it's primary or hazardous voltage to a safety extra low voltage that's earthed, or between a primary circuit and a reinforced part, this also needs to have reinforced insulation as well. Okay. For the next part, we're going to use a flow chart to help us determine creepage and clearance. This, if anything, throughout this whole presentation, I find to be the most useful part. So we had a customer who gave us some specifications for a design. They listed out the different things that they needed to meet for safety purposes and for their PCB. And we were able to use this flow chart to determine the right levels of creepage and clearance for that particular design. So let's take a look at how this flow chart works. So first, we're going to look at the insulated system for safety against electrical shock. So again, this is for systems in which there is a user interface in which they could come in contact with the electrical voltages. If your system is completely sealed, has no user interface, you don't need to worry about this. But if you do, let's see what we can do here. So we're going to start first with the clearance. So the first thing we do with the clearance is we need to determine the mains transient voltage, we need to determine the pollution degree, and we need to determine the altitude above sea level. So once I know what those are, the next thing I can do is I can decide whether it needs basic or reinforced insulation. So if it needs basic insulation, then I can refer to this table within IEC 60664, table F2. And then I check the altitude, and based on the altitude, there is a multiplication factor that I can use. Okay, next, if I determine it needs to be reinforced isolation, then I can refer to a one step higher from table F2. So if I determine on table F2 that I need a certain spacing, but then it needs to be reinforced, I basically just go to the next level down of spacing. Okay, for the creepage, I need to determine three factors. So I need to determine the working voltage, the pollution degree, the material group, and then I do the same set of questions, whether it needs to be basic or reinforced insulation. If it's basic, then I refer to IEC 60664, table F4. If it's reinforced, I do the same thing as before, 2 times basic insulation. If my PCB doesn't need safety, creepage, and clearance, then I can use high voltage spacing, and there are a few different parameters that I can look at. So I can look at the general PCB guideline, and that's IPC 2221B. If I have a targeted end equipment, I can find the IPC standard for that specific end equipment. Or if there are other exceptions, which we're going to talk about here in a little bit, I can do a high pot test, or there are other routine